In this video, we're going to introduce the idea of a ring homomorphism. When you first learned about groups, you learned that there are these functions from one group to another that have a special property that if I take two elements of G, call them A and B, and multiply them and then apply the map, I get the same thing as if I apply the map to both elements individually and then multiply in H. Having that property makes a map a group homomorphism. Of course, I should point out that this property has to hold for every A and B belonging to G. So if that property holds for all A and B belonging to the group, then we call phi a group homomorphism. The idea of a homomorphism, if you'll recall, the word comes from root words for same and then shape. So having a homomorphism is like saying that two groups have the same shape, or at least that they have some structural properties in common. They don't have to have exactly the same shape if phi is not an isomorphism. Okay, so in this video we're going to talk about the idea of a ring homomorphism. And we start in pretty much the same place. So here's a definition. Let phi from R to S be a function from one ring R to another ring S. And for this video, as always, we're going to assume that the rings are commutative with unity. But that doesn't have to be the case. You can define ring homomorphisms for any rings, non-commutative rings included. It's just for now we're going to focus on the case of commutative rings with unity. All right, so we say phi is a ring homomorphism if it has the following two properties. Number one, if x and y belong to R, then phi of x plus y is equal to phi of x plus phi of y. That's like saying that phi preserves addition. And then number two, if x and y belong to R, then it's also true that phi of xy is equal to phi of x times phi of y. So in other words, phi preserves multiplication. And just to be very clear, the fact that I'm using the word if to quantify both of these statements, this is really saying for all x and y belonging to R and for all x and y belonging to R. In other words, phi has to always preserve addition and always preserve multiplication to qualify as a ring homomorphism. But once we know these two things, we can actually say quite a bit about the relationship between the structure of R and the structure of at least part of S. So we'll explore that in the next video, but first let's talk about some examples of ring homomorphisms. So first of all, let's talk about the map from the ring of integers to the ring of integers defined by phi of x equals 2x for all integers x. Okay, so let's verify whether this is a ring homomorphism. So first of all, if x and y both belong to z, then phi of x plus y is equal to 2 times the quantity x plus y. And we're going to check whether that's the same as the result if we had just taken phi of each element and then added the results together. So phi of x is 2x and phi of y is 2y. Adding those together gives me the same thing as 2 times x plus y. So these two are the same. And they're the same for all x and y in the set of integers. So that means at least phi preserves addition. Now let's check that phi preserves multiplication. If x and y are integers, then phi of xy, that's equal to 2 times the quantity xy. And phi of x times phi of y, that's equal to, let's see, that's 2x times 2y. And wait a minute, that's not the same as 2xy. That's 4xy. These two are not the same, not unless x or y is 0, which means they're not going to be equivalent for all choices of x and y. So these two are not going to be the same in most cases. So that means that phi is not a ring homomorphism. So in this case, phi is not a ring homomorphism. Too bad, because it seems like something this reasonable, just doubling every element, ought to be a ring homomorphism. But it turns out that disrupts enough of the ring structure of the integers to fail to qualify as a homomorphism. So we have a function here, it's a very nice function, and it is a homomorphism of additive groups, but it's not a ring homomorphism between the integers and itself. All right, so that's example 1. Example 1 was kind of a letdown. All right, so let's try something else now. Example 2. Let's define a function phi from, and I'm going to say let's go from the rationals to the polynomial ring on the rationals. And we're going to define this by phi of a equals a for all a in the rationals. I was tempted to use x there, but we're not going to use x because we're already using x to represent our indeterminate or our variable in the polynomial ring. Okay, so this time we're just going to send each rational to itself, but it's itself in a much larger ring. And here, it's not too much trouble to show that phi is a homomorphism. Really, the point is to point out that this homomorphism exists, rather than to surprise you or wow you with the fact that it's homomorphism. So phi of a plus b is equal to a plus b, because that's just what phi does to a plus b. It leaves it alone and embeds it in this bigger ring. And that's equivalent to phi of a plus phi of b. No big surprise there. Same with multiplication. Phi of ab equals a times b, and that's a times b is the same as phi of a times phi of b. Okay, so this map does check out. Phi is a homomorphism. It may not seem like a particularly exciting one, but it's kind of nice to know that it's there, because one thing that this indicates, anytime we have a homomorphism from one ring to another, and that homomorphism is 1-to-1, and we didn't verify that here, but you can easily show that this map is 1-to-1. So I'm just going to jot that down. Phi is 1-to-1. Because it's 1-to-1 and a homomorphism, meaning it preserves the ring structure of the domain, we often call that a ring embedding. And sometimes it's nice to remember that one ring is embeddable inside of another. Okay, but I feel like I owe you a more entertaining example, so I'm going to try for one here. Let's see about a map. And this time I'm going to go from something called Q adjoin root 2 to itself. And for the uninitiated, which at this point is probably most everybody, Q adjoin root 2, this is a field. It consists of all numbers of the form a plus b root 2, such that a and b are rational numbers. Now, one thing I have not done is I have not established this as a field. It's not obvious at all, because you take one of these numbers, how do you know the reciprocal of this is also expressible in the form rational plus rational times root 2? We're going to dodge that question for now, but we are going to address it later. For now, I'm going to ask you to believe me momentarily that that is a field. It has all the necessary structure to be a ring. It is commutative. You probably can tell that without too much effort. And every element has, or every non-zero element has a multiplicative inverse. That one takes a lot of checking, but we can do that later. Anyway, how are we going to define this map? We're going to define phi of a plus b root 2 to equal a minus b root 2. And this may sound somewhat familiar. We call this a conjugation map. Because we're sending each element to its conjugate in Q adjoin root 2. All right. So is this a homomorphism? Well, the fact that I'm calling it a map kind of suggests that it is. I usually only use the word map for homomorphisms. But we're going to check that here. We're going to show that this really is a homomorphism. So what happens if we apply phi to the sum of two elements in this field? And we have to be careful here and make sure that we are actually writing down the sum of two elements of this field. So the first one I'm going to call a1 plus b1 root 2. and then the other one a2 plus b2, square root of 2. All right. Now, before we figure out what phi does to this, we need to make sure that this element is in the form prescribed here. All right, so how are we going to do that? Well, we're going to say that's the same thing as phi of a1 plus a2. That's going to be the rational part. And then the square root of 2 part is going to be b1 plus b2, square root of 2. And there I'm just combining terms using the distributive property. These two add together to give me this, and then these two terms add together to give me a1 plus a2. So now I'm in this standard form here, so I can apply phi directly to this element. Of course, all of this assumes that any element of this field can be expressed in this way in only one way. That's another thing I'm glossing over for right now, just for the sake of the example. But anyway, when we apply phi to this number, we're going to get the same rational part, but the opposite square root of 2 part. All right. Now, does that agree with what happens if I apply phi to each element individually and then do the addition? Will that be the same thing? Well, this gives me a1 minus b1 root 2. This gives me a2 minus b2 root 2. And if I combine these, I get a1 plus a2 minus, and it looks like I do get the same thing. Yay. Okay, so these two check out as being equivalent. So at least my phi preserves addition, but what about multiplication? That's a little bit trickier. But the way this works out is kind of cute, actually. So what if I have phi of a1 plus b1 root 2 times a2 plus b2 root 2? Again, to figure out what phi does to this, I need to get this into some kind of standard form. This is the standard form here, up here at the top. I need to get this into rational number plus another rational times root 2. So I'm going to do a little bit of math inside of the parentheses first. This is a1, a2. The next part seems to be a1, b2, square root of 2. Next part is a2, b1, root 2. And then finally I have b1, b2 times square root of 2 times square root of 2. That's 2. I'm going to put that there just for housekeeping purposes. So it looks like my rational part is a1, a2, plus 2 b1, b2. And then my square root of 2 part is a1, b2, plus, really I think I should call that b1, a2. I just feel like I want to keep the subscripts in order more than I want to keep the letters in order for some reason. Okay, so that's my standard form, and then when I apply phi, I just switch the sign on the square root of 2 part. So that gives me a1, a2, plus 2 b1, b2, all right, minus a1, b2, plus b1, a2, root 2. And that's that. So that's what happens if I multiply, then apply phi. What if I go the other order? What if I apply phi to each element, then multiply? Well, that's going to give me a1 minus b1 root 2. And this other one's going to be a2 minus b2 root 2. And then let's multiply, see if we get the same thing. a1, a2 minus a1, b2 root 2 minus b1, a2 root 2. And then finally it looks like I have plus b1, b2 times 2. And combining like terms, I have, I guess it's not really combining like terms, it's more like I'm combining rational parts and combining square root of 2 parts. But it looks like I get the same thing. Look at that. That's just so satisfying. I realize it's probably also a little tedious, but anyway, what we've discovered here is that this map, this function, it really is a homomorphism from Q adjoin root 2 to itself. And it's a non-trivial one, which for some rings can be pretty darn hard to find. But the thing I really love about this example is this is actually an example of something that happens all the time in field theory. And this is just by way of preview without revealing any of the relevant theory behind this right now, because that's going to come a little bit later. But this Q adjoin root 2, this is called an extension field of the rationals. Again, I haven't proven it's a field yet, but we will show that. And it's called an extension because it's a field that properly contains the rational numbers. All right, so it's an extension field. And the thing being added on is the square root of 2 here. Now that square root of 2 is a very algebraic object. It's a root of the polynomial x squared minus 2, which we will discover over the rationals that is an irreducible polynomial. But this polynomial really has two roots. It has square root of 2 and negative square root of 2. So the thing that this map is doing is it's really taking this element here, a plus b square root of 2, and it's taking a and b and pretty much leaving them alone, but taking square root of 2 to negative square root of 2, and that negative gets folded into the sign on this entire term. So really what we're saying is leave the rationals alone and take square root of 2 to its little partner here, because this root here is always partnered with this other root. So we're going to discover that anytime we have an irreducible polynomial that has more than one root in an extension field, there's always going to be a homomorphism, in fact an isomorphism, which takes one of the roots to another root. In fact, there will always be an isomorphism taking this root to any of the other roots.